Okay, hello everyone. So last video we looked at some of the five main assumptions for OLS to be the best linear unbiased estimator. Now we want to move into more of the computation aspect of running regression models in R. You've probably used the LM command in some of your other courses, but essentially it's very easy to run a regression in R. So if we have simple regression with one explanatory variable, with one of the R's built-in data sets for women that looks at the height, how height varies with weight, we can use the LM command. Our outcome variable is weight, squiggly line, regressed onto height. And we get a summary of the regression model will give us this output where we have our estimate, which is our beta parameter, our standard error, which is the amount of uncertainty surrounding our point estimate. We have a t-value and we have a p-value, which basically is telling us how statistically significant from 0 this estimate is. We'll go over some of the interpretations here real quick. Just for review, you're asked to do this in the lab, so make sure you know what's the coefficient. The coefficient is the beta coefficient, is the estimate. This is going to show us the strength of the relationship between our x and our y. It tests for statistical significance as well as the economic meaningfulness. So in our regression here of weight on height, the way we interpret the coefficient is a 1-inch increase in the height of a woman is associated with a weight increase of 3.45 pounds. And we could also say a 1/2 foot increase is 6 inches in the height of a woman is associated with a weight increase of 20.7 pounds. Okay, so we can look at whether or not those findings are statistically significant from 0. And the way that the hypothesis test here is we're testing the null hypothesis that the coefficient is equal to 0. That is no effect. So when we have a very low p-value, rule of thumb alpha less than 0.005, the way we interpret this is that there's a rejection of the null hypothesis of no effect. In other words, we're saying that we do find a statistically significant effect that's different than 0. And this p-value or this alpha value of 0.05 indicates 5% risk of concluding that a difference exists when there is no actual difference. Okay, so this should hopefully be review. The R squared, which is produced, which we saw produced, it shows how much of the variation of our outcome variable y can be explained by our x's. Obviously, the higher the value of the R squared or adjusted R squared means that your covariates x are giving you a better prediction or explanation of variation in y. So for instance, a 0% R squared of 0.00 would show that our explanatory variables cannot explain any of the variability in the outcome variable. Our F statistic is showing our general overall fit of the model. Is essentially testing the null hypothesis that running a model with only an intercept is statistically the same as the model that we actually run that includes our x's. So if we have a low p-value, again, alpha 0.05 or less, indicates that the model that we're actually running is better than if we just have an intercept-only model. Okay, so we can use the F-test to kind of see which which variables we should include in the model. Higher the F-test, the better that the model is fit. So okay, so that's the canned approach using the LM canned routine. If we wanted to see what's actually going on here, we could look at the function, what's inside LM. But I want to give you another approach where we can estimate the beta coefficients for the intercept parameter and also the slope parameter, which is the beta coefficient on height. So this is equivalent to our slope and our y-intercept. So we can manually obtain these parameters, the coefficients as well as the standard errors manually by hand. And that's what I want to do to show you exactly what's going on in R behind the scenes. And we're going to be using some matrix algebra, so it's a little bit technical, but I think it's important to understand what's going on. So recall from the first video, in order to get the parameter estimate of interest, we need to essentially minimize the sum of squared errors, where we're representing the residuals here as the yi minus xi b hat, and we're minimizing the squared value of this after summarizing. In matrix notation, the sum of squared residuals, E prime E, is going to be, we can expand this squared term here, where we have our y minus x b hat, x beta hat, and multiplied by y minus x beta hat. And this is going to be the sum of the squared residuals in matrix notation. We're going to get our beta estimates by, again, minimizing these the squared estimates here, taking the derivatives with respect to beta, and we're going to set the equation equal to 0. And this is going to give us our first order conditions, first order condition FOC, after we, again, set this to 0 and we minimize solving for the derivative of the sum of squared errors. We have some algebra here to manipulate the equations, and we want to essentially solve for beta. And so whenever we're looking at our beta hat, what we're going to be solving in matrix notation is this x prime x inverse times x prime y, okay? And this is just the theory behind deriving our beta parameters. We can calculate this by hand inside of R. So if we have just create just a very small data set just out of thin air, we'll have 2 observations for our x. 2.4 and 3.1 is our values. These ones here represent our constants. We'll have two rows, 2 columns. Our y is going to be our outcome variable. Again, there's 2 observations, 4.1 and 5.4. So for the x prime, what we're going to do is transpose x, t of x. So we'll take t of x, and you can do this in R and follow and see what the output looks like. Then we want to get the next part is x prime x. And again, we're just manually entering this x prime x. We're going to inverse and then x prime y. Okay, so that's what we're doing now with the matrix operators. So we have the transpose x, which is x prime, transpose x multiplied by x. This is, again, x prime x multiplying the matrices. Now, to get the inverse, we're going to use the solve function. So solve transpose x times x is essentially x prime x inverse. And then the last part we need to do is the x prime y. So again, transpose x times the y. And if we put it all together, again, we want x prime x inverse x prime y. We're going to basically put these parts together into one uniform function. And this is going to give us our point estimates for our beta. Okay. So as an empirical example, we'll look at the weight, the women data again, looks at the height and weight of different women in the sample. So to create our x, we're going to combine together a set of ones, which represents our constant, and the x variable height. We're going to bind them together and create a matrix called x. Our outcome variable, we're going to create a matrix for women's weight. So we have our x and y, as we've done before. Now we're going to minimize the sum of squared errors, again, doing the x prime x inverse x prime y. We have our x, we have our y. So we just need to transpose x multiplied by x, wrapped in a solve function to get the inverse, and again, multiplied by x, transpose x times y. So we can round this equation to 2 digits, and what we're going to get is our beta hats, okay? So if we want to combine our information, we'll C-bind the information in beta hat, and we're going to label the first value in beta hat is going to be the beta point estimate for the intercept, beta 0, and then the beta 1 point estimate for height. Okay, so we have our estimate 87.52 and 3.45. So this is, again, created the first part of our output equation that's done automatically in R, our estimate negative 87.5, and height point estimate is 3.45. So we can replicate that. The next part is we need to get the standard errors. And this is going to look a little bit nasty, but we essentially need to recover the variance covariance matrix and take the square root of this diagonal, which is giving us the variance or the uncertainty surrounding each of our beta hats that we're predicting. And then on the off diagonal is just the covariance between our different betas. Okay, so to actually recover the the VCV matrix, we need to define, we need to obtain our the variance around our point estimates given the set of explanatory variables, and we have our familiar squared error terms here, e prime e, and then multiplied again by our x prime x inverse. And here we're going to divide 1 over the difference between the number of observations in our data and the number of parameters k. Okay, so we can recover the variance on this diagonal variance covariance matrix with this following equation. And we know the equation for these predicted errors here, epsilon, and that is just yi, observed yi minus the predicted yi. And the predicted yi is, again, the difference between the intercept and beta 0 and beta 1 xi. Okay, so this is how we're going to formulate the variance around our point estimates. We can calculate, so we have our observed y minus our y-intercept, beta 0, and then times our beta 1 parameter times women's height, okay? And we have our n, number of observations will be n rho, and our number of parameters will be the number of x's. And so we can then create the variance covariance matrix with the formula 1 over n minus k. We have our squared residuals here, transpose residual times residual, and then we're solving using x prime x inverse. Okay, so here's how we actually would calculate it in R. And to get the standard error, we just take the square root of the variance, and that's going to be the diagonal, again, of the variance covariance matrix. Take the square root of that diagonal, and this is going to give us our set of standard errors. We then will calculate the p-value, which is using the information of our coefficient estimates and the standard errors that we've obtained in the previous couple steps. And we use a t-test, which we use with the pt in R, and we show whether or not at certain values, whether or not the standard error uncertainty estimate surrounding our coefficient estimates is going to be statistically significantly different from 0. So we can combine our coefficients, our standard errors, and our p-values together. And again, we will essentially replicate what our canned routine regression model does for us. And we can see the p-values are essentially 0. So they're very highly statistically significant. These effects of height on weight is statistically significantly different from 0. We can use the scatter plot. If we just do ggplot and we plot height versus weight, and we can use the geom smooth to create the linear regression model. If you remember from the graphical example, we just did this as well. So in R, we use this geom smooth to do the same thing, and we have the method of LM, and it will automatically run the regression line for you. This is the built-in R function. We can also do manually, where we have our intercept is the coefficient of beta 0, which we derived already. The slope is the x parameter for x on height, which we derived already. And just manually entering the intercept and slope, we will have our line drawn for us. We can also add the standard errors to show that this is significant from 0 if we wanted to. Okay, so that's just a very quick run through of how we are manually are able to calculate or execute OLS regression in R using matrix algebra. Going forward, though, we'll just use the canned routine. It's obviously a lot easier to go to run the models, but I think looking at this matrix notation helps get a sense of the intuition of the complexity that what used to be done by hand is now able to be done automatically in R for us. So, okay, so stay tuned for the next video. Give just a brief example of OLS and just going over how we can look at the regression results and do some model diagnostics and interpret some of the results.